This video is brought to you by mywayteaching.com.
In this part, let us study one of the important law of thermodynamics, that is first law of thermodynamics. Okay. So we already studied that internal energy of a system can change through two modes of energy transfer, that is heat and work, isn't it? So let us consider delta Q as heat supplied to the system by the surroundings. So delta Q is heat supplied to the system by the surroundings. And delta W, work done by the system on the surroundings. We consider delta W as the work done by the system on the surroundings. Similarly, we can take delta U as a change in internal energy of the system. Okay, change in internal energy of system. Okay, so the general principle of conservation of energy implies that delta Q is equal to delta U plus delta W. That is nothing but heat supplied to the system by surroundings is equal to the work done by the system on surroundings plus change in internal energy of the system. So in wordings, so you can see here the energy supplied to the system goes in partly to increase the internal energy of the system, that is delta Q, and the rest in work on the environment, that is delta W. So that is what the first law of thermodynamics is. So that energy supplied, it is utilized to change the internal energy and to work done on the, yes, to work done on the surroundings. So that is delta Q is equal to delta U plus delta W. The general law of conservation of energy apply to any system in which energy transferred from or to the surroundings is taken into account. So we can apply this law. So let us put this first law in other way. That is, we can write that like this also. That is delta Q minus delta W is equal to delta U, isn't it? So now the system may go from an initial state to the final state in a number of ways. Which means you just consider example, that is change the state of a gas from P1 V1 to P2 V2. Okay, change the state of a gas change the state of a gas from P1 V1 to P2 comma V2. Okay, so here we can first change the volume of the gas from V1 to V2, keeping the pressure constant. So we can first to go to the state by when we change the volume by keeping pressure constant, that is P1 comma V2, and then we can change the pressure from P1 to V2 keeping the volume constant, then we'll get P2 comma V2. So alternatively we can first keep the volume constant and then keep the pressure constant. Since internal energy is a state variable, that delta U, change in internal energy of the system, depends only on the initial and final states and not on the path which is taken by the gas to go from one to the other. However, that delta Q, that is heat supplied to the system by the surroundings, and delta U and delta W, that is work done by the system on the surroundings, depend on the path taken with to go from the initial state to the final state. See, from the first law of thermodynamics, that is from the equation that we have studied just now, this equation. Okay, it is clear that the combination, that is delta Q minus delta W, is however is taken through a process in which delta U is equal to 0, which means the change in internal energy is 0. Isothermal expansion of an ideal gas is a better example for this. In that particular case, delta Q is equal to delta W, that is heat supplied to the system is used up entirely by the system in doing the work on the environment. It is not used to increase the internal energy of the system. Suppose the if the system is a gas in a cylinder with a movable piston, the gas is moving the piston, it will do work, isn't it? Since force is pressure times area and area times displacement is volume, work done by the system against the constant pressure is given by, okay, we can write the work done as P into delta V, where delta V is the change in volume of the gas. So, for this particular case, we can write the equation, that is the first law of thermodynamics, as delta Q is equal to delta U instead of delta W, P into delta V. As an application of this particular equation, we can consider the change in internal energy for 1 gram of water when we go from its liquid to vapor phase. In that particular case, when we measure the latent heat of water, it is found to be 2256 joule per gram. That is, for 1 gram of water, delta Q is equal to 2256 joules, isn't it? At atmospheric pressure, 1 gram of water has a volume of 1 centimeter cube in liquid phase and 1671 centimeter cube in vapor phase. So we can write delta W into delta W is equal to P into Vg minus Vl. We know that pressure is 1 point atmospheric pressure 1.013 into 10 raised to 5. Vg minus Vl is 1670 into 10 raised to minus 6, which gives the value as 169.2 joules. So delta U is equal to 2256 minus 169.2 2086.8 joules. So here we see that most of the heat goes to increase the internal energy of water in transition from the liquid to the vapor phase. Okay. Now let us study what is specific heat capacity. Just suppose an amount of heat, that is delta Q, supplied to a substance changes its temperature from T to 2 T plus delta T. In that particular case, we can define heat capacity of the substance as which is represented by S is equal to delta Q by delta T. We expect delta Q and therefore heat capacity S to be proportional to the mass of the substance. It could also depend on the temperature, that is, a different amount of heat may be needed for a unit rise in temperature at different temperatures. To define a constant characteristic of the substance and independent of its amount, we divide S by the mass of the substance. So S is equal to S by m, that is 1 by m delta Q by delta T. So where S is known as specific heat capacity of the substance. It depends on the nature of the substance and even it depends on its temperature. So the unit of this specific capacity is given by joule per kg per Kelvin. This is the unit. If the amount of substance is specified in terms of moles instead of mass in kg, in that particular case we call it as heat capacity per mole of the substance, which is represented by the letter C, which is known as molar specific heat capacity of the substance. So that is equal to S by mu, that is 1 by mu delta Q by delta T. Okay. So, like yes, C is independent of the amount of substance. It depends on the nature of the substance, its temperature, and even it depends on the conditions under which heat is supplied. So, if you consider the unit that we use to represent this molar specific heat, joule per mole per Kelvin. Okay.